All right, so here is a practice problem. And the question is, how much heat energy is needed to completely boil 47.35 grams of water if it starts as a liquid at 100 degrees C? Alright, so what this is referring to here then has a lot to do with that graph that you did. We looked at as we add heat energy to a sample of water, and if you start down here where we're below 0, say this is 0 degrees here, then you have ice up until you reach 0. Then things level off into a plateau while you're melting the ice. Then once you have everything in the water form, you can heat it up. So during this period here, you're adding heat, but there's no temperature change because that's where it's melting. All the heat is going into breaking apart the molecules and making those melt. I know you remember from physical science, or really even from earlier science classes, that solids, the molecules are kind of stuck in one place, right? They're stuck in place, right? They're wiggling, but they're stuck next to each other. But when you turn into a liquid, they're still touching but moving around each other. Okay, so you had to put some energy in there to get them to sort of unlock, unstick. And that's what's happening right here. We're putting energy in there to get them to unstick. They're still touching. Then once you get them moving fast enough, we're adding heat and raising the temperature. Once you get them moving fast enough, eventually they'll reach a point where they're no longer even going to be touching. They're going to fly apart. Well, that takes some more energy. So while you're boiling it, then we get another plateau. And then finally, in the steam, you can raise the temperature again. Okay, so that's that graph we did. And each of these regions, this direct relationship part of the graph here, direct relationship because it's a straight line with a positive slope, this direct relationship portion has the same equation as this direct relationship portion and this direct relationship portion. All of these have the equation Q equals, that's the heat energy, mass times the specific heat times the change in temperature. So that equation is we used right here and right here and right here. Okay? And so while there's no temperature change, because in these plateau regions the temperature's not going up. So for those, then we use this equation here. Q equals mass times the change in enthalpy. And so that then fits any place there's this plateau, like here and here. And so all we need to know now is, well, we know the mass is given to us. All we need to know other than that then, if we're using this equation, we have to figure out the change in temperature, and we have to look up the specific heat. Or really, this is called heat capacity. Specific heat is a particular kind of heat capacity. And for this one, we have to know what the change in enthalpy is. All right, now I gave you on your graph for this class what the change in enthalpy was for the conversion or changing from something, the transition from being liquid to gas, the boiling, where the boiling's happening. Okay, you got a question? Well, sure, go ahead and tell me. That's good. So in this region right here, okay, where we're changing from liquid to gas, the delta H is equal to 334 joules per gram, correct? Yes? Now you don't have to memorize that number. If you need to use that number, I will give it to you on the test. Somewhere. It might not be the first place you look, but it's on there somewhere for you to use. Okay? And if I give you a calculation that requires this, the specific heat's going to be there. You have to remember every substance has a different set of specific heats and changes in enthalpy. Okay? And every substance has at least three different specific heats and two different enthalpy change values. Okay? The three different specific heats are for the different physical states, solid, liquid, and gas. And the two enthalpy changes are where you change from solid to liquid or liquid to solid and from liquid to gas and gas to liquid. Okay? Now there is a number for sublimation, but we don't make it that complex. Okay? Remember, there is sublimation too in addition to those phase changes. All right? So this is the number we need. If we're boiling something, well, while we're boiling, we said, that's this region right here, there is no temperature change. The temperature isn't going to increase. So we can't use this equation. We don't have any temperature change. We have to use this equation when we're changing physical state. So this is the equation we're going to use. Once we identify the equation, now it's plug and chug. Okay? So here's Q equals mass times the change in enthalpy. Now, just a word of warning and a word of notice here. If you fail to write down the correct equation, I'll count off points for that. All right? If I were giving you a test on this might be worth 5 points just for writing the equation. A point for Q, a point for equals, a point for mass, a point for times, and a point for the change in enthalpy. Okay? If the problem is worth 20 points, that's 5 of your 20 points right there. Okay? Now, it's okay to use either the dot or the time sign. Either one is fine. All right? Now we want to plug. So we've got the formula. We write it out. Now we're going to plug in what we need to do. Well, Q is what we're trying to find because the question's asking me how much heat energy. Well, Q is our measurement of heat energy. Okay? That's how we measure it. That's the variable that means heat energy. So we need to know the mass. The problem tells us the mass. 47.35 grams. And we're going to put that over 1 because there's nothing on the bottom, but there is going to be something on the bottom here to keep everything lined up nice and neat. And we already identified what our change in enthalpy is. Okay? 334 joules per gram. And just like with the last problem we were doing when we were doing the combustion, now we're ready to simplify by canceling out what we can cancel out. So we're going to cancel out grams, and that's all we can cancel out. We're left with joules, and joules is a measurement of heat energy. Okay, so we know we probably set it up right if we cancel everything in the right way. It helps us to keep up with things. And later in the semester, these kinds of problems get more and more complex. So if you keep up with canceling units and canceling the units, and if you end up with the units and species you're looking for, you know you pretty much set it up right. All right? So now we're ready to do the math. So this is where your calculator comes in. Everybody has to have a calculator for the test. 47.35 times 334. Now, I'm just multiplying the two things on the top in this case because everything on the bottom is ones, and dividing by ones just gives us the same number we started with. So we're kind of leaving that step out. But I come up then with, let's see, 15,814.9. Keeping my units over here. You have to write the units with every number. Can't leave the units off. Can't leave the species off if there are any. In this case, there isn't any, but if there are species, you have to keep them. And now we're going to look for our significant digits. In multiplication and division like this, we're going to look for all the measured and calculated numbers. That's these two numbers here. And we're going to find the one of those two, or however many there are. In this case, there's only two. We're going to find all those measured and calculated numbers, which one has the least digits. This one has 4, and this one has 1, 2, 3. So we want to only keep 3 digits in our final answer. And you start from the left and find the first non-zero digit. That's almost always, every case I can think of, that's always going to be your first significant digit. And count 1, 2, 3, and that's where you stop. And we underline everything else because that tells us what we're going to round off. In this case, we're getting rid of a number in the ones place. And anytime you get rid of a number in the ones place, you must write your answer in this class. It's required. You lose points if you don't. You must write your answer in scientific notation. And so we're going to move our decimal place then to between the first and second significant digit. So we're going to move it from here to 1, 2, 3, 4 places to the left. If we move it 4 places to the left, that's going to tell us what our exponent is on the 10 that we're going to multiply by. So now we're going to draw, and we've underlined our insignificant digits. That's some points. Draw an arrow That's how we show that we're rounding off. If you don't show the arrow, you're not showing you're rounding off. You lose points. Then we're going to say our decimal place is going here, so that's 1.58. We've got a 1 here, so that's less than 5. That 8 doesn't change. Times 10 to the, if we moved our decimal place to the left 4 places, that's a positive 4 exponent here, joules. And if you'll help me out and put a box around it, I'll have a better idea of what your final answer is. You know, you could have something closer to the final answer than I realize, and I don't even know it's the final answer sometimes. So you got to put your box around it to help me figure it out, and you lose less points that way. Potentially. I mean, you might not, but you potentially lose less points if I can see that you did some things right. I can give you points for it. Any questions? Okay, be careful about your J's. On the last test, I saw a lot of J's that looked like, or the quiz, I don't know, that looked like 5s. Okay? Just write neatly for me when you're doing the test, okay? All right, help me out. All right, any questions about that? All right.